The relationship between light and gravity is fundamental to our understanding of black holes. In order to tie these ideas together, we will have to relearn the concepts of gravity, space, time, and light that we've been presented in our favorite movies, TV shows, and other great works of art. Popular culture doesn't always get the science behind these concepts right, but it's surprising how scientific accuracy informs spectacular effects in movies like Interstellar. The scientific foundation for black holes has been built by hundreds of scientists contributing ideas throughout history. But one unmistakable scientist was responsible for the biggest developments: Einstein. Einstein's theory of gravity describes the gravitational attraction between massive objects, such as a star or a black hole, by associating the force of gravity with an equivalent curvature of space, sort of like this curved sheet. All physical objects, including rocket ships and individual particles of light called photons, travel on curved spacetimes similar to the curved path that these marbles follow. In this simple demonstration, we have an up and down direction defined by the Earth's gravity, which gives us the effect of the marbles orbiting around the central depression. In outer space, near a star or a black hole, we don't have Earth's gravity holding the marbles down on the curved sheet. Instead, we recognize gravity as curvature of space and time. This curved sheet provides valuable insight into how we can imagine the warping of space-time. A black hole is a region of space where the force of gravity becomes so strong that the curvature of space-time prevents light from escaping. In this curved sheet model, imagine that a marble represents light. If the marble is aimed away from the center and tossed with a high enough speed, the marble is able to escape from the depression in the center. The region outside of a black hole, or normal star, is like this. Light that is emitted from objects in the neighborhood of a black hole are still able to escape. But there is a special spherical boundary surrounding the black hole, which scientists call the event horizon. Once a marble falls within the event horizon, it must continue falling inwards. You could try to aim a marble outwards, but you'd never be able to make the marble go fast enough that it can escape. To some people, the concept of a black hole is terrifying. A black hole represents an inescapable vortex whose strength can stretch astronauts into spaghetti and even eat whole stars. Falling into a black hole is irreversible, and once inside, there is no opportunity to escape, ever. To characterize this fear of black holes, people use the word melanoheliophobia, the fear of black holes. Much of that fear is misguided, as you will see, and black holes come in various flavors that are not equally dangerous. That's good news if you are among those who suffer from melanoheliophobia, so sit tight. There is another misconception about black holes, that they suck things towards them. All astrophysical objects, like the sun, the earth, and black holes, have gravity, and gravity is an attractive force. This means that just as marbles are attracted by gravity to the earth, so too are they influenced by the gravity of other objects. If we throw a marble directly towards the earth, or the sun, or a black hole, then just like the marble on this curved sheet, the thrown marble travels directly towards the central depression. The strength of a gravitational depression depends on the mass of the object causing it. A star and a black hole with equal mass, even though they are different sizes, produce the same gravitational attraction far from their centers. If this depression represents a star, then the star's surface is big, and the marble enters the star and is burned up. Traveling directly towards a star is a recipe for crispy bacon. Now, let's pretend this depression represents a black hole. The gravity is exactly the same, but the black hole is much smaller than the star, so marbles can travel deeper into the depression before we lose track of it. When a marble enters the black hole's event horizon, the curvature due to gravity prevents it from escaping, and it becomes lost to us forever. So even though directly traveling towards a star is a recipe for crispy bacon, traveling directly towards a black hole is a recipe for no bacon at all. Instead of traveling directly towards a star or a black hole, we can instead travel safely around it in orbital paths similar to how this marble can be made to circle or orbit around the depression. Since the curved sheet in our demonstration has friction, the marbles eventually lose energy and fall in towards the center. However, in space there is virtually no friction, so it is possible for orbits to be stable for extremely long periods of time. For instance, the Earth has been orbiting the Sun for close to 5 billion years, and will continue to orbit it for several billion more years. The idea that gravity is really just a curvature of spacetime is a tough concept, which requires some knowledge of Einstein's theory of gravity called general relativity, which we will be introduced to later on in this course. However, we can still get a taste of black hole physics by making use of an older, less accurate description of gravity created by Sir Isaac Newton. In fact, several 18th century physicists were able to deduce the idea of a star whose light can't be seen using just their knowledge of Newton's theory of gravity along with the value for the speed of light. Since the concepts of light and gravity are so important for understanding black holes, we will review the basics of light, Newtonian gravity, and some elementary physics principles as our starting point.